Last time I gave you a quick run-through of some of the aspects of function field theory. So in particular, I defined what it was. So it's another way to talk about one-dimensional algebraic varieties. I explained what a place is in such a function field, and gave you some concepts after that. So in particular, there was the concept of a divisor and the divisor of a function. So such a divisor was a combination, formal sum of places where the coefficients are integers, and this AP is supposed to be 0 for all but finitely many places. Now what I want to do today is to finish the introduction to function fields. So in particular what I want to do is to formulate a version of the Riemann theorem, and if time allows I will have say a little bit about what happens if you take the function, the constant field of the function field to be finite. So there are some special arithmetic coming in there. So let's see if I can manage that. We're definitely to Riemann today. So the point about these divisors is that it allows you to select functions from the function field in a special way. So what we do is we want to look at so-called L spaces or Riemann spaces, and they are collections of functions satisfying this. Yeah, if you want to be completely accurate, then we should really say, okay, we don't allow 0 here, and then we add it later. This is if we want to be completely correct. So this is going to be a linear vector space over a constant field, and the dimension over the constant field of this Riemann space denoted by small l of g. Now there's a small source of confusion here, because some of the books take this definition of little l of g, but there are also books where they use this as a linear series. They use this to create an embedding into a projective space. And if you do that, then it's quite natural to say that the dimension of the projective space you're embedding into is the L of G. So that would be one less. So you really have to be careful if you pick a book which one is meant. Yeah, but I'll stick to this one. Okay, so what can we in general say about this? So there are a few examples, a few cases where you can compute this without any prior knowledge of the function field. So in particular, if we now just pick 0 for the divisor, so we pick the empty sum there. So what does it mean then? Then this condition boils down to that the divisor of your function should be effective, as it is called. So any coefficient in this divisor, in this case, should be positive or 0. So it really means that we are looking at all the functions without poles. And that is one of the things that's only possible if you look at the constants themselves. So in particular, this is going to be 1. So this is one example which we always can compute. And there's one more case, which is kind of gives itself. This is namely, if the degree of the divisor is negative, then also the L space is completely determined. And the reason for this is that, yeah, suppose we have an element, a function in this L space. So what it says is that this inequality has to be satisfied. And now if we take the degrees on both sides of this, this inequality, which was this partial ordering on divisors that I mentioned last time. So the degree of this whole thing will then be forced to be positive but the degree of any principal divisor was 0. So this is just exactly the same as the degree of G itself. So if I can really find any non-zero elements in this L space, then the degree of G is forced to be non-negative. So this is one more case where we can say something. And another property that we will going to use, not today, but when I will talk about decoding, is that if we have this partial ordered divisors, then we'll have that the L spaces of one is included in the other. It's immediate from the definition. Okay, so the goal is now to say something more about this dimension. And this is what the theorem of Riemann-Roch will do for us. But before we get there, we'll get some intermediate results. And we will see where that will take us. So, in general, we do not know at this point what the dimension of a L space will be. But what about if we stick to a very particular example? So we take the rational function fields and we look at a very simple divisor, just a multiple of this point at infinity, this P infinity, this place at infinity, I should say. So what do we have in this case? Well, this L of MP, if we look at the condition that any element in here has to satisfy, let me do this here, so the divisor of F plus M of P infinity should be effective. So what does it mean? It means that this function F, we just move it to the other side, it just means that if you look at the divisor of this function, then it is not allowed to have any poles, negative valuation, at any place except at P infinity. And at this P infinity, it may be minus M or more. So, a function having no pole whatsoever except at infinity is a polynomial. It has to be a polynomial. And this tells you something about the degree of the polynomial. Because the valuation at infinity, it was essentially the degree with a minus sign. So what this means is that this is nothing but a linear space of polynomials in the indeterminate, and the degree of this polynomial should be less than or equal to m. That's what it is. So this is just a space of polynomials of degree m or less. And in particular, we can see what the dimension is going to be. It's m plus 1. Okay, now, it turns out that this is very good motivation for following lemma, which tells that in general, the following is going to be true. It's going to be at most the degree of the divisor plus 1. Yeah, so we see that in that case there, this is actually inequality, but in general we only have this inequality. And there is an even stronger property, namely that the distance between these two numbers is, if we fix the function field, it's going to be, it has an upper bound, independent on the choice of divisor. So in fact, this led to a possible way to define the genus of a function field. Namely, what we take is, we look at all the differences here, the degree of G plus 1 minus this L of G, where G is a divisor. Yeah, so you run over all divisors and you take the maximum of this expression here. So what this says here is that this number here is going to be non-negative, but also this is going to be a finite number. That is what Riemann showed. So this is in fact going to be a non-negative integer. And this is called the genus of the function field. Now we'll later see that we can define this genus in a different way that you may have seen before. So this is the genus, and then we have a consequence of this, which is a theorem by Riemann. It's the following. So it has two parts. So we are given a function field f, we have given a divisor. We just write down what it says here. So in the first place we get immediately from the definition we get this inequality. That is clear once we know that this is defined. But more interesting is that there exists a constant C such that for all divisors G with the degree large enough, meaning that the degree is larger than or equal to C, and then what we have is equality. Yeah, so this L of G is actually equal to this expression. And that is the real content of Riemann's theorem here. Yeah, so not only do we have an inequality, but for any divisor of large enough degree, we have equality. So this constant C only depends on the function field, not on the choice of divisor. Now, and this is already good enough to say something about the genus in practical cases. So this is a much weaker result than Riemann rock, but nonetheless I will show you that this leads to some estimates on the genus in general. So, what I'm going to do is look at an example. And it's the so-called Hermitian function field. So what I do is I choose my field of constant is a finite field with q squared elements, and the field is going to be generated by two elements satisfying an equation. Let me write it down so I have the same as in my notes. Okay. So it's the following equation. So the trace from fq squared to fq, so to say, of x2 is going to be equal to the norm of fq squared to fq. That is a way to interpret this equation. So,
can you please repeat your last sentence?
This?
The norm,
yeah, okay, so a way to think about this is that if you look at the finite fields, the trace map from fq squared to fq, it will send an element alpha to the q plus alpha. Because this is a Galois extension, and the Galois group is generated by Frobenius, so taking the qth power. And similarly, the norm would be just the same here, taking the product of these two, that's alpha to the q plus 1. So this we don't need this today, but the point of choosing this field is that this is going to have a lot of rational places. That is the point of choosing this constant field. So we'll see later that this in fact has q cubed plus 1 rational places. But we'll see that another day. So for now what we need is that we want to say something about the genus of this function field. Now the only tool we have is Riemann's theorem. So the idea will be to pick a very specific divisor. So for divisor we need places, and places can be described by valuations. So what I will do is I will write down a particular valuation, V infinity, from F to Z. And one can check that the following will define valuation. So if we know what it does on generators, we're already well on the way. So we're going to do this. So x1 is being sent to minus q, and x2 to minus q plus 1. Now to see why this actually defines a valuation, you would have to go into details, but let us at least check that this definition is compatible with the equation I had. If it's not, then definitely we're in trouble. But let's see what we have here. So we have here the equality of these two elements from the function field. So taking the valuation on this side here, so x1 has valuation minus q, so it will give you minus q times q plus 1. Taking the valuation on this side here, we have a sum here, so we can use the triangle inequality, and in fact we are in the situation where the valuation of these two functions is distinct, so it's actually an equality. So it means that the valuation of this is minus q plus 1, and this will be q times minus q plus 1, so this one is the minimum. So we see that indeed the valuation of those two sides is the same. Now it's not quite enough yet, but at least it tells you that this makes sense. So let's denote the corresponding place by q infinity. Q because p infinity was already one in the rational function field. Now if you think more geometrically, you can also look at this as an equation defining a plane curve. Then if you look at the projective closure, you see that there's one more point popping up, because if you homogenize this and put in the third variable to 0, this x1 is 0. So you have the projective points 0, 1, 0. And that's actually another explanation of this one. That's exactly where this place comes from. Okay, so let us now pick as a divisor a multiple of this place, n times q infinity. So what can we say about this? So what I'm saying is that maybe I don't know exactly what this is, but I can look at a certain span of monomials in here. So what I'm going to investigate is functions of this type, a monomial in these two variables, and see what it takes for I and j, but that this function is an element in there. So computing this valuation at q infinity, looking at what this condition then means, you get the following condition. But that is not quite enough, because we cannot allow other poles. So this is to be the only possible pole of a function here. And to make sure of that, we can say that we just pick I and j non-negative, because then this is just a polynomial expression, and again we need to check the details that this is in fact the only place where either x1 or x2 has a pole. So under these conditions we are going to find a set of monomials that is inside here, and in particular the linear space generated by it will be a subspace. Now I want to say something sensible about the dimension of this subspace, but this is not quite enough yet then, because I have here a linear dependence between monomials. So to avoid that, I'll just assume that the second exponent is less than q. Because if it were q or larger, you could use this equation to rewrite it. Yeah, so that's why these conditions come up. These are just to make sure that I am in the space, and this one comes up to make sure that all these monomials are linearly independent. Okay, so we just make a picture of this. We have I here, and j here, but the picture looks roughly like this. So we have a q here, and then we have this m, let me see. So we have here this inequality, which somehow translates into this one. So this is iq plus jq plus 1 is equal to m. This line segment is j is equal to q, or q minus 1 if you wish. And then what we are looking at is all the points, all the lattice points inside, they correspond to these monomials. So what I can say is that this L mq is going to be larger than or equal to, now I have to do this counting. Count exactly how many lattice points there are in here. And in fact, I will leave it as an exercise to work out the exact details, but let me give you one little piece of advice. Don't do it for any m. Just choose m of a very particular form, namely of the form mq times q plus 1. Like this. Because if you do that, it turns out that some of these intersection points, they are all have integral coefficients, which makes the counting a bit easier. So for these kind of expression, you can then show that this one is at least going to be the number of lattice points, which is going to be, if you do everything correctly, 1 plus mu q plus 1. This term is more or less counting everything in this rectangle, and then we have to subtract something because of this triangle there, which is going to be 1/2 q minus 1. Like that. That is going to be the result. And this here is of course exactly the degree of this. So what we have here is an estimate on the dimension of this particular L space. But that implies, from the definition, from Riemann's theorem, this implies an upper bound for the genus. So the argument is like this. If we choose mu large enough, the degree of this divisor will be larger than this c. We don't know what it is, but we just choose mu large enough. So then equality holds. And then comparing it with what we have there, we get an upper bound for the genus. Like that. Okay, so we can already find upper bounds on the genus using only this result. And let me see how I deal with the time. I cannot resist elaborating a little bit more. So it turns out that with a very similar argument, you can prove a more general result, not just for this Hermitian function field, but for a much more broader class of function fields. So let me state the result here. And the proof is very similar to what we did here. So kind of function fields I'm looking at are of this form. We again have two elements generating it. Let me denote it by x and y, so we don't confuse them with the others. And we have some polynomial equation now. And this polynomial, let us be very explicit about it. So it has the form summation alpha ij, and then we have x to the power I, y to the power j, and I'm summing over some index set I, and this is chosen in such a way that for any element from the index set, this coefficient is not zero, just to avoid trivial cases. So this is as small an index set as makes sense. Yeah, so for this particular polynomial, we can then define so-called Newton polygon, which is going to be the convex hull of this I. Yeah, so we have to imagine we make a picture, we draw all the elements of I in the plane, and then we take the convex hull. And this is called the Newton polygon. Okay. Now what is then the statement going to be? This Newton polygon which is actually a rational polytope in the language of the previous lecture. So let me say it looks like this. We have some points lying on it. These are the elements of I, say. We take the convex hull and we get here this delta F. Now the theorem states that the genus of this F is less than or equal than the number of, let me just write it. So we pick all the ij in z squared such that I, j is in the interior of this Newton polygon. Yeah, so what we can do is compute exactly, well, what kind of lattice points do we have inside? Yeah, not on the boundary, but really lying inside. If you count them, that gives an upper bound for the genus. And this is an old result. This is, at least if you look over the complex numbers, this is from 1896, if I remember correctly. In characteristic P, the story is a little bit more subtle. But anyway, for the complex numbers, this has been known for a long time. And this has a number of consequences that you may have seen before. So if we look at the total degree of this polynomial, then there's a result by Plucker saying that the genus is at most 1/2 d minus 1 d minus 2. And you see that, well, proof by picture. So if we only know that what the total degree is going to be, then what we can say is, well, here we have this Newton polygon, and we can, so to say, estimate it by this triangle. Because if the total degree is d, this will have to lie inside this triangle. And counting the number of interior lattice points of this triangle, we get this. So this is an immediate consequence of this. And there's another one. If we define the y degree of f to be n and the x degree to be x, then it is the result by Riemann that the genus is less than or equal to n minus 1 times n minus 1. And again, we can do a proof by picture because, well, we have this Newton polygon here somewhere. And this just gives you enough information to approximate it by a rectangle. And the number of interior lattice points in this rectangle is exactly this. So you see that this is a very nice way to get these classical results. You have this general result here. Okay, so we could have used this as well for this Hermitian case. Now, if we want to say more, if we want to really be able to compute the genus, yeah, we need a little bit more of machinery. So Riemann's theorem only takes you that far. So in order to get an equality in Riemann's theorem for any degree divisor, you need to introduce differentials. Now, I don't want to spend too much time on it, so let me just give you the computational rules that we will need. So the point is that differentials can be defined in several ways. For example, in this textbook of Steepenote, we will talk about Weyl differentials. But there is also another notion of differentials that were in the second lecture today. Was also mentioned. So what we really want is, we somehow want a derivation here. So what we're going to do is we are going to look at symbols of the form Fi dgi. This is going to be a differential in general, where Fi and gi are elements from the function field. And then we want some rules, namely that this d is linear over the constant field. And we want that it is a derivation. So if we have a product, then we want it to be equal to this expression here. Well, such a derivation exists. We can show that it's actually unique. And what we then want is, yeah, somehow to figure out what differentials on a function field look like. But the main result is that if we take all these kind of differentials, this effect a one-dimensional vector space. Over the function field. And this is a well-known result for differentials. Can be generalized to higher dimensions, but if we just look at what happens in the proof here, yeah, so there are a few steps, but the first is that we look at what happens in a rational function field case. So if you look at any expression of this type, where the functions are from the rational function field, yeah, this is just a product rule. So it means that if you would happen to have a quotient of polynomials there, you can get rid of that quotient by this rule, essentially the quotient rule. And then what you have is an expression where all these things, all these elements are polynomials. Okay, but then by using this linearity, we can further expand this where all these gi's now are monomials, powers of the variable x. But then again, using this product rule iteratively, you can always boil things down to that any differential is some expression, some function, rational function times the x. You just go through the motions of these rules, using product rules, sum rules, those kind of things. So it is really, it's true in this case. Yeah, but well, how can we then do this in general? So what you have to do is now, if we have a general function field, what we're going to do is pick an element such that the extension f over fx is finite, but also separable. Yeah, so what you do then is you pick an element, such that is a finite extension. That's always possible, because that was in the definition of a function field. But now I also want that this is a separable extension. And this cannot always be done. So here I need this assumption I made yesterday that this is a perfect field. Otherwise, there are counterexamples. And this is also the reason that if you want a more general theory, that these y differentials are better suited. Yeah, but for the case that we were looking at, these separable, these perfect constant fields, then this works. Yeah, and then how do you continue? Well, we just say that if it is a separable extension, it can be generated by one element. So if it is separable, then there exists a y now, such that f is nothing but fx comma y, and we have some equation of lowest degree in y connecting them. Yeah, and then this equation gives rise to, using now again this rule, that you can connect differentials dx and dy. So we write it like this. This relation is then a consequence. So it means that we can express dy in terms of dx. And then continuing like that, we can also show that any differential for the function field f can be expressed as a multiple of dx. Yeah, one detail, I'm dividing here by something if I want to express dy in terms of dx. But fortunately, it was a separable extension, so this is not going to be zero. This may happen in general, but not in this case here. So this is really a non-zero element from the function field. Okay. Now the next thing that I will need to formulate Riemann-Roch is so-called divisor of a differential. So let's now pick any differential. And let us also pick a place of the function field. And let us say that Tp is a local parameter for P. So what I then can do is, in fact, this T of P turns out to be a separable, what is called a separating element. So we could choose x to be equal T of P. So the classification of all possible choices of x here is just that they are not allowed to be pth powers of elements in F if the characteristic is P, and if the characteristic is 0, well, we can choose any non-constant. Fine. Divisor like this. We run the sum over all places, and then we have evaluation of P of this function zp, z times P, this formal sum. And it turns out that this really is a divisor, and moreover, one should also check that the choice of local parameter does not matter. But this one can show that. So this is a well-defined object, independent of the choice of this, and also it is really a divisor. Now what this one-dimensional property really tells you is that if I would have chosen any other divisor, any other differential, it's going to be a multiple of this one. Yeah, that means that if you then look at the divisor, it's just going to be the divisor of a function plus the one I have. So in other words, up to this linear equivalence of divisor, this is going to be unique. So this is why this is often called the canonical divisor. This is in some sense only one choice, up to equivalence. Okay, but now we're nearly there, because this will enable us to formulate Riemann-Roch theorem. So we have the following formulation. Yeah, so we were going to look at this L of G again. So we have a function field going on in the background. And before we had only an inequality for low degree G, and we had an equality for large degree. But now we have an equality always. So what we get is you have the degree plus 1 minus the genus of the function field. And then this is the term that gives you equality always. So it's another L space, but now W minus G, where W is the divisor of a differential. Now this is a very useful theorem. Now in particular, it allows you to refine the argument I just gave, and you can then investigate a little bit better when you will have equalities in these kind of theorems. So I erased the result by Baker, but analyzing this carefully, you can now see when you have equality in the genus, and also as a consequence in these cases. So, but let's look at some other consequences of this. So in the first place, if we choose the divisor to be 0, what do we get here? We get that L of 0, which was 1, is going to be the degree, which is 0 plus 1, minus the genus, plus the L of W. Yeah, so in other words, what we get is that L of W is the genus. Now I have avoided looking at spaces of differentials for now, but what this really means is that if you look at all differentials not having any poles, this will form a vector space of dimension G. That is what this will boil down to. So this is maybe a more familiar definition of the genus, the dimension of regular differential forms. But I haven't explained exactly how this connects to differentials yet. Yeah, so that is one thing. And another thing is that if we choose now this G equal to this canonical divisor W, what we get is L of W, which we just computed, the genus, is equal to the degree of G plus 1 minus the genus, and then plus the L of W minus G, which is L of 0, so plus 1. So what we really get is, I should have written a W there, what we really get is that the degree of W is equal to 2G minus 2. Yeah, so the degree of a canonical divisor is 2G minus 2. And the fact that this degree does not depend on the choice of differential is also not surprising if you remember that it was unique up to linear equivalence. And the degree of any principal divisor is 0, so which is why the degree is an invariant there. So this tells you exactly what the degree is. Okay, so let me see. There's one more thing that I will need tomorrow, and I will define AG codes. So let me tell you that. Let's see if I can talk a little bit about what happens if the constant field is finite. Let us see. So what I want to talk about next is residues of differentials. So what we can do is, given a differential, given a place, and for now let me just assume that the degree is 1, so it's a rational place to make it a little bit easier. And I have a local parameter. And what I can do is I can write my omega in a very specific form. So what I can do is, well, in the first place, I know it will be of the form some function times this dt of p, just as I had before. But now I can write this function here by saying, okay, I'm going to look at a kind of Laurent development. So it's like this, and then there's some remainder. So this function here may well have pole at p, have negative valuation, but then what I can do is I can start developing this in a Laurent series, but I don't really need the whole series. I only need here some negative exponents, and then there's a remainder which will not have a pole anymore. So it's in the local ring there. And these A of n, they're going to be in the constant fields. And then what you can define is the residue at P of this differential is A minus 1. That is the residue. We take the coefficient of Tp to the power minus 1. Again, there are a lot of remarks to make here. For example, that doesn't depend on the choice of local parameter again. That is not so easy to show directly, which suggests that maybe residues should be defined in another way, and they can be. But this is a very computationally suitable way. So this residue is just this coefficient. It doesn't depend on the local parameter, but it does depend, of course, on the place P. Now also, if the degree of the place is not 1, it's larger, you can define it. But let me avoid the technicalities here. So what happens, roughly speaking, is that this doesn't work anymore, but it does if we replace this field by the residue field. Then you can still do all this. Then you get again a coefficient, which is now from the residue field. But then we have to take the trace down to the constant field. And then that is going to be the residue in that case. But we will only need it for rational places. Then the main result about these residues is the following. So there's the famous residue theorem. Which tells you the following. Well, I can formulate it very succinctly like this, simply tells you that the summation of all such residues over all places is 0. Now this is a remarkably nice result. So we have all these residues, but adding them together will necessarily give you 0. Now, a way to see why this makes sense in some setup is the following. These residues, they came up in Cauchy's residue theorem. So in complex integrations, these residues turn up when you are determining integrals over a closed curve. So let's say a circle. Now we are looking at this algebraic setting here, so that means we should look at compact Riemann surfaces. Now we take the simplest possible compact Riemann surface, we are just looking at the Riemann sphere here. Now suppose now that we want to determine the integral over some small closed curved circle there, and we are looking at this differential here, f dz. Yeah, so what happens according to the residue theorem is that, okay, this is a differential, it has residues at certain points on the Riemann sphere, and let us just for simplicity suppose that we have chosen this curve in such a way that there are no residues in this part, inside, so to say. But inside, it doesn't really make sense. It only makes sense if I give this an orientation. But choosing the orientation one way or the other only will differ the minus sign in this integral. Yeah, so if I take it in one way, I get, according to Cauchy's residue theorem, the sum of all residues inside up to a scalar factor, which is 0 because there are no residues inside. But now if I turn the orientation around, I will get exactly the sum over all residues. Yeah, and that is why this residue theorem follows from Cauchy's residue theorem in this case. Yeah, and then you can lift this argument to other compact Riemann surfaces. But it's a much more general result that really holds also if my constant field is positive characteristic. Okay, I see I have like 5 more minutes. So let me then tell you a little bit about what happens in case I have a very special constant field. Nothing like C, but now I'm going to look at what happens if F is a finite field. So in that case, these concepts like rational places and so on become really very restrictive. So in fact, what we then can do is given a function field over such, let me really write that this is over a finite field with q elements here, we can look at the set, or rather the cardinality of the set of all places of degree 1, all rational places. So now I have, so to say, a new invariant to look at. Yeah, before I introduced the genus, and now I have a new thing, new object, the number of rational places. And it turns out that these two have a very close interplay. So in particular, there's a very nice result. Connecting them in an inequality in the following way. So what we have is that this number is going to be less than or equal to q plus 1 plus 2 root q times the genus. And this is the result by Clase and Beelen. So in particular, if we have a rational function field, then what we are looking at is, well, this genus is 0, so this term is not going to be there. But what we can say in the case of genus 0, well, we were looking at a line. Yeah, so the genus 0. So the geometric picture is we have a line, but then it really means that we can index the rational places by elements from the constant field, and we have an extra one, namely, let's say at infinity. So you see that in that case, you really get q plus 1, and equality holds. But in general, we have this extra term. And this is a deep result. This really follows from a Riemann hypothesis-like analogon for the function field case. So this is a deep result. And in general, one can improve it a little bit. So what you can do is you can take the integral part of 2 root q. And this is an improvement using very elementary arithmetical techniques by Say. But it again uses this specific structure of a certain zeta function, the Riemann, in the function field case. And this is a very good improvement if q is not a square. And then in general, one cannot hope to get a better upper bound in the sense that there are examples where these are tight, where equality holds. So in particular, I mentioned this Hermitian function field. Then it turns out that equality holds here. So in general then, we cannot hope to get a better result, but when you investigate this, people found out that this only can be sharp if the genus is not too big. And therefore, it makes sense to try to look at what happens in the limiting case. So what happens if I take the lim sub over all possible function fields? The genus will have to tend to infinity, and I look at this quotient. And this constant is called Ihara's constant. So, and still a lot is not known about this. So this is still a topic of active research to try to compute this one explicitly for a given q. So let me tell you a little bit about what is known. So it is known that it is less than root q minus 1. It's a so-called Drinfeld-Vladet bound. And what it really means is, if just looking at this inequality up there, we can see immediately that this lim sub is at most 2 times root q. But in fact, what we see here is that asymptotically, as the genus tends to infinity, this 2 root q can be replaced by root q minus 1, in that sense. So a little bit more is known. For example, if q happens to be a square number, then equality holds. And this is a result by Ihara, and later independently by Swassmann, Vladet, and Zink. But in general, not much more is known. Yeah, there are a few other results. There are in general, it is known, for example, that this is positive. But otherwise it gets sketchy. Yeah, there are for very specific q, there are some values. If q is a cube, there is a lower bound, but we don't know what the answer is. So I don't even want to guess what it might be. So here we don't have equality, but if q is not a square, it's still a very open problem. Okay, so let me stop now. So tomorrow I will start introducing codes and also related to these results up here. Let's see what we can do with them. Thank you.